So in this short optional video, really just for fun, I want to point out an interesting consequence that the contraction algorithm has about a problem that's in pure graph theory. So to motivate the question, I want to remind you of something that we discussed in passing, which is that a graph may have more than one minimum cut. So there may be distinct cuts which are tied for the fewest number of crossing edges. For a concrete example, you could think about a tree. So if you just look at a star graph that is hubs and spokes, it's evident that if you isolate any leaf by itself, then you get a minimum cut with exactly one crossing edge. In fact, if you think about it for a little while, you'll see that in any tree, you'll have n-1 different minimum cuts, each with exactly one crossing edge. The question concerns counting the number of minimum cuts. Namely, given that a graph might have more than one minimum cut, what is the largest number of minimum cuts that a graph with n vertices can have? We know the answer is at least n-1. We already discussed how trees have n-1 distinct minimum cuts. We know the answer is at most something like 2 to the n because a graph only has roughly 2 to the n cuts. In fact, the answer is both very nice and wedged in between. So the answer is exactly n choose 2, where n is the number of vertices. This is also known as n times n-1 divided by 2. So it can be bigger than it is in trees, but not a lot bigger. In particular, undirected graphs have only polynomially many minimum cuts. And that's been a useful fact in a number of different applications. So I'm going to prove this fact to you. All I need is one short slide on the lower bound, and then one slide for the upper bound, which follows from properties of the random contraction algorithm. So for the lower bound, we don't have to look much beyond our trees example. We're just going to look at cycles. So for any value of n, consider the n cycle. So here, for example, is the n cycle with n equal to 8. That would be an octagon. And the key observation is that just like in a tree, how removing each of the n-1 edges breaks the tree into two pieces and defines a cut, with a cycle, if you remove just one edge, you don't get a cut. The thing remains connected. But if you remove any pair of edges, then that induces a cut of the graph corresponding to the two pieces that remain. No matter which pair of edges you remove, you get a distinct pair of groups, distinct cuts. So ranging over all n choose 2 choices of pairs of edges, you generate n choose 2 different cuts. Each of those cuts has exactly 2 crossing edges, and it's easy to see that's the fewest possible. So that's the lower bound, which was simple enough. Let's now move on to the upper bound, which a purely combinatorial fact will follow from an algorithm. So consider any graph that has n vertices, and let's think about the different minimum cuts of that graph. What we're going to use is that the analysis of the contraction algorithm proceeded in a fairly curious way. So remember how we defined the success probability of the contraction algorithm? We fixed up front some min cut a comma b. And we defined the contraction algorithm, the basic contraction algorithm, before the repeated trials. We defined the contraction algorithm as successful if and only if it outputs the minimum cut a comma b that we designated up front. If it outputs some other min cut, we didn't count it. We said, nope, that's a failure. So we actually analyzed a stronger property than what we were trying to solve, which is outputting a given min cut ab rather than just any old min cut. So how is that useful? Well, let's apply it here. For each of these t minimum cuts of this graph, we could think about the probability that the contraction algorithm outputs that particular min cut. So we can instantiate the analysis with a particular minimum cut, ai, bi. And what we proved in the analysis is that the probability that the algorithm outputs the cut, ai, bi, not just any old min cut, but in fact this exact cut, ai comma bi, is bounded below by, in the end we made a sloppy inequality. We said it's at least 1 over n squared, but if you go back to the analysis, you'll see that it was in fact 2 over n times n-1, also known as 1 over n choose 2. So instantiating the contraction algorithm success probability analysis without all of the repeated trials business, we show that for each of these t cuts, for each fixed cut, ai, bi, the probability that this algorithm outputs that particular cut is at least 1 over n choose 2. Let's introduce a name for this event, the event that the contraction algorithm outputs the ith min cut. Let's call this SI. The key observation is that the SIs are disjoint events. Remember, an event is just a subset of stuff that could happen. So one thing that could happen is that the algorithm outputs the ith min cut. And by disjoint, we just mean that there's no outcome that's in a given pair of events. And that's because the contraction algorithm at the end of the day, once it makes its coin flips, it outputs a single cut. These are distinct cuts. It can only output at best one of them. Why is it important that these SIs are disjoint events? Well, with disjoint events, the probabilities add. The probability of the union of a bunch of disjoint events is the sum of the probabilities of the constituent events. If you want to think about this pictorially, you can just draw a big box denoting everything that could happen, omega, and then these SIs are just these blobs that don't overlap. So S1, S2, S3, and so on. Now the sum of probabilities of disjoint events can sum to, at most, 1. Right? The probability of all of omega is 1, and these SIs have no overlap and are packed into omega. So the sum of their probabilities can only be smaller. Writing that formally, we have that the sum of their probabilities, which we can lower bound by the number of different events, and remember there are t, different min cuts for some parameter t. For each min cut, ai, bi, a lower bound on the probability that that gets spit out as output is 1 over n choose 2. So a lower bound on the sum of all of these probabilities is the number of them t times the probability, lower bound, 1 over n choose 2. And this has got to be at most 1. Rearranging, what do we find? T, the number of different min cuts, is bounded above by n choose 2. Exactly the lower bound provided by the n cycle. The n cycle has n choose 2 distinct minimum cuts. No other graph has more. Every graph has only a polynomial number, indeed at most a quadratic number of minimum cuts.